Okay, it's 5 o'clock, hopefully, well, where I am, 2 o'clock in California. Welcome back, everybody. And it's a pleasure to introduce Mary Wootters from Stanford University. And she's going to finish the afternoon session with her talk on sharp thresholds for random subspaces. Please go ahead.
Thanks. Yeah, thanks for the invitation, and thanks, Prasad, for the introduction. Yeah, it's really great to get to talk to you guys today. So yeah, I'm going to talk about sharp thresholds for random subspaces with some applications to coding theory. And this is based on joint work with Jonathan Mosheeff, Nick Resch, Nogaran Zui, and Shashwat Silas. Okay, so what is this talk about? So the title had some coding theory jargon in it, but basically what this talk is about is it's about combinatorial properties of random subspaces over finite fields. Right, so I'm just going to take like a uniformly random subspace over some finite field. It's a bunch of points. It's a discrete thing. And I'm wondering what sorts of combinatorial properties does this bunch of points satisfy? So for example, is it the case that no Hamming ball contains too many of these points? Something like that. And there are some applications to these types of properties I'm interested in that come from error correcting codes, but hopefully what I have to say will be of interest even if you are not into error correcting codes. Hopefully these are just sort of interesting probability questions. So the plan for the talk is I'm going to give a quick intro to what sorts of combinatorial properties I'm interested in, and a little bit about why I'm interested in them, although not too much. And then I'm going to tell you a threshold theorem for what properties are satisfied with high probability by uniformly random subspaces. So basically, for these sorts of properties that I'm interested in, like not having too many points contained in any Hamming ball, it's going to be the case that as the dimension of the subspace goes from small to large, like very large subspaces are very unlikely to satisfy these properties. Like there'll be tons of points in some Hamming ball. Very low dimensional subspaces are quite likely to satisfy these properties. And I'm kind of interested in like, what is the threshold in between? Like, what is the point where a subspace goes from being very likely to being very unlikely to satisfy such a property? And I'll tell you that there is a sharp threshold, turns out, for a certain very broad class of properties. And also I can give you a characterization of that threshold. So that will sort of be the second part of the talk. And the third part of the talk is an application of this characterization to LDPC, or low density parity check codes. But from a sort of probability perspective, the punchline of this application is basically that you can transfer concentration of measure type results that you would be able to prove for uniformly random subspaces, that you can basically transfer those almost for free to more structured random subspaces, or at least to a particular distribution of more structured random subspaces. And that's basically going to fall out for free from this characterization threshold theorem that we'll see. Okay, so that's the basic plan. Let me get started by telling you just about random subspaces and a few nice properties that they might satisfy. So what are the sorts of questions that I'm interested in? Okay, so first, random subspaces over finite fields. Like, what do I mean by that? Throughout this talk, this Blackboard bold F here is going to denote a finite field. If it's been a while since finite fields, don't worry. It's fine if you just want to think about this as being F2. So that is just 0 and 1 with arithmetic mod 2. That'll be fine for almost all of the talk. So just think about F as being F2, if you like, or any finite field. And I'm interested in subspaces over this finite field F. So subspaces V that are subsets of F to the n. And here subspaces over a finite field, I just mean the same thing as subspaces over the reals, just some set that's closed under addition and scalar multiplication. So just a quick example to make sure we're on the same page. It's like, here's an example of a subspace of F2 to the 6 of dimension 2. I take 2 basis vectors. So each of these basis vectors is a binary vector of length 6, and then I look at their span. So their span contains 0, the first basis vector, the second basis vector, and then their sum mod 2. So this is going to be my subspace. It has size 4. Okay, so the reason, or one reason that I'm being so pedantic about what do I mean by a random subspace is for the rest of this talk, I'm going to draw subspaces over a finite field by this cartoon here. So the points here are meant to indicate that it's some kind of discrete finite set, and the little picture of a plane in R3 is meant to indicate that there's some type of linear structure. So that's what this cartoon means, but this is like extremely misleading about the geometry. Like they don't look like this, don't think they look like this, think they look like this. So the reason I did this example is just to emphasize you should be thinking about these things as like subsets of the hypercube, not like this, but I'm going to draw them like this anyway. Okay, so that's a random subspace, those are subspaces over finite fields. I'm interested in random subspaces. Here, when I say random subspace, I'm going to mean uniformly random subspace. And so a uniformly random subspace over a finite field is just a uniformly random subspace over a finite field. And so there's finitely many of them, just take a uniformly random one. Cool. Okay, so now that we know what we're talking about, uniformly random subspaces over finite fields, we can ask some questions about them. So here are a few questions that you might ask. Question 1, what is the closest that any 2 points in V can be to each other in Hamming distance? So here, Hamming distance, the Hamming distance between 2 vectors x and y is just the number of coordinates on which they differ. So I can ask, out of all of the points in this subspace, like look at every single pair of points, look at how far apart they are from each other, like what's the closest any 2 of them can be? And in particular, is it the case that with high probability, none of them are too close? So that's one sort of question you might want to ask. Another sort of question in a similar vein is, what is the maximum number of points of my subspace V that lie in any Hamming ball of radius Pn? So here, I don't mean in any fixed Hamming ball, but kind of like a worst case Hamming ball. So I'll draw my random subspace, and then I'll take my Hamming ball and I'll kind of like move it all around the subspace and try to capture as many points as possible. My question is, like, when I do this, what is the maximum number of points that I can capture? So that's some random variable, depends on the randomness of my subspace. And again, I want to maybe be able to make some statement like, you know, as long as the dimension is not too big with high probability, probably no Hamming ball will capture too many points, something like that. Okay, another question you might want to ask, I could just go on all day, like I could replace the Hamming ball with some combinatorial rectangle, like S1 cross S2 cross ... cross Sn, where each Si is a subset of my finite field of size not too big. Here, this is the one example where you should not think of F as being F2, but maybe some bigger finite field. And again, I can ask the same question, like what is the maximum number of points of my random subspace V that live in any one of these combinatorial rectangles, if I just like look at all of the possible ones. And again, hopefully I could make some statement of the form, with high probability, there are not too many points in any combinatorial rectangle. Okay, so those are a bunch of questions you can ask. Why might you ask these questions? Well, I kind of think they're interesting on their own right, just in their own right as math questions. But my original motivation for studying these comes from error correcting codes. So I'm not going to go into this very much at all, but just one slide to maybe wave my hands a little bit about why I might care about these questions. So this first question that I talked about, the distance between any 2 points, this is actually a very classically studied question in the theory of error correcting codes. Another way to say this question is just, what is the distance of a random linear code? So here, code just means subset of f to the n. And so random linear code means random linear subspace of f to the n, of f to the n. So this is like exactly what we're studying. And distance just means the minimum distance between any 2 points. So this is a very classical notion that people are interested in coding theory. Super briefly, one reason why is that imagine you're like using these points here for communication. So to each of these points, I'm going to associate a message, and I'm going to want to send this message across some noisy channel. If the points are all really far apart, then if there's a little bit of noise, let's say I want to send this point and it gets perturbed a little bit, then if they're all really far apart, I can sort of round back to the point I was interested in, and I can like correct the noise. So that's the basic idea behind an error correcting code. And so it's an interesting question to ask, like, what is the distance of such a set? The second question about Hamming balls, this is basically asking what is the list decodability of a random linear code? So list decodability, again, is a classical notion in coding theory. And the basic idea here is that any particular Hamming ball of a fixed radius might represent, in this communication setting that I said before, might represent like the set of points you might plausibly be confused about. Like I didn't know which one the sender meant to send. And if you can show that not too many points live in any such ball, you can sort of limit the amount of confusion that you get at the end of the day. Similarly, this question that I asked about combinatorial rectangles, this also has a name in coding theory. It's called list recoverability. The motivation is basically the same under a different error model. This combinatorial rectangle is like the set of things you might get confused about. And if there are not too many points in your subspace that live in the combinatorial rectangle, then like, hooray, you don't get confused. So that's why you might be asking these questions if you come at things from a coding theory background, which I do. And why you might be asking them about random linear codes in particular, or these like random subspaces in particular. Well, actually for some of these questions, just for existential results, it's, if you want to make an existential result, like there exists a linear code with good distance, random linear code is a pretty good place to start. And also for that same reason, they can be useful in constructions. Like you take a really little random linear code that gives you like the best existential thing, and then you can sort of use that as a building block in some bigger, more efficient construction. Okay, so these questions come up. I'm not going to say too much more about why one cares, but if you're interested in, please ask me after the talk. And for now, let's just forget about the motivation and just like focus on these questions, like what properties do random subspaces satisfy? Okay, so what do we know about these questions? So like I said, these questions have been studied for a while in the context of coding theory. So by now we know a lot. So here's a real quick lit review about these three questions in particular. So this first question, how far apart are any 2 points in a random subspace? Like I said, this is a very classical question, and the answer to it, or at least one side of the answer to it, is called the Gilbert-Varlamov bound. So here's what we know. So here on the x-axis, I'm drawing the rate of the code, or sorry, the dimension of the subspace. So here's some jargon. Instead of measuring the dimension of the subspace, I'm going to normalize it by the dimension of the ambient space. So I'm going to be looking at this fraction k over n, so subspace dimension divided by ambient dimension. And I'm going to call this the rate in coding theory language. That's the sort of the communication rate of the code. And so here I have the dimension of the subspace on the x-axis. So up here, I have like the full dimensional subspace, just the whole thing, all of f to the n. And down here, I just have the trivial subspace, just 0. And on the y-axis, I have the probability that a random k-dimensional subspace satisfies this property that I'm interested in this case, that it has distance at least delta, aka all pairs of points are at least delta n apart. And what we know is that there is some special threshold in the dimension of the code, so that if I back off by a little bit from that threshold, so if I look at a subspace of dimension just a little bit less, then with super high probability, I'm going to satisfy this property, aka there's going to be no pair of points that's too close to each other. All pairs of points are going to be far apart. On the other hand, if I go a little bit above that threshold, so I have a slightly higher dimensional subspace, then all of a sudden it becomes extremely likely that I do not satisfy this property. That is, that there are 2 points that are really close together. Okay, so that's sort of what's known for this question. And again, this is a sort of a pretty classical result. It's not too hard to see. You could probably do it yourself if you get bored later. Okay, how about the next question? How many points lie in any Hamming ball? This turns out to be a lot more tricky. There's still ongoing work on it. There's still things we don't know. But the basic cartoon looks roughly the same. There's some threshold rate. And if you back off from that by a little bit, so you look at a slightly lower dimensional subspace, then with really high probability, you'll satisfy this property. Not too many points will be in any Hamming ball. And if you go a little bit above that, so you look at a slightly higher dimensional subspace, then with really high probability, you're not going to satisfy this property. There's going to be some Hamming ball that has tons of points in it. Right, so same basic picture. And we can ask the same question, what's known about points that live sort of in a combinatorial rectangle? Once again, this is actually an even more open question. We don't quite have everything pinned down, but if you zoom way out, the basic cartoon looks roughly the same. There's some threshold rate. If you back off by a little bit, then with really high probability, the property is satisfied. And if you go a little bit above that, with really high probability, the property is not satisfied. Okay, so the story so far, this is all just kind of introduction stuff. I asked you 3 questions about random subspaces over finite fields. And I told you a little bit that they were motivated by coding theory. And I told you that they all have sharp thresholds. So that's sort of the background, and I'm going to go forward from here. But before I move on, are there any questions?
I have a quick question, Mary. So I think you mentioned it before. So far, the results you mentioned hold for f2 to the n, or they're typical for any finite field?
For any finite field. Yeah, well, so this one doesn't even make sense over f2, actually. Like here, you need a large enough field. Mm-hmm. Yeah, and these ones, this certainly works over any field. this, depending on the parameter regime, works over some fields better than others, and larger ones get a little more dicey. But yeah, there are results of this flavor over lots of fields. Great question.
Thanks.
More questions?
What is h of p?
Oh, sorry. H of p down here, this is the entropy of p. So p times log 1 over p plus 1 minus p times log 1 over 1 minus p. For binary codes. Over larger fields, replace this with the Q-array entropy, which is roughly the same thing, but base Q. Sorry about that.
Okay.
Yeah, the identity of this threshold is not going to be super important for this talk. The main thing I wanted you to take away from this is that it has this kind of threshold behavior.
In the last picture about the rectangle, you drew the curve a little differently. Is that meant to indicate something?
Yeah, I guess I mean, these are all curves that I drew by hand in PowerPoint,
Yeah.
so don't take, they're not meant to be very precise, but yeah, I drew this one like scaled a little bit out to indicate that we don't, the answers that we have are a little bit less tight for this question. In particular, there's a lot more wiggle room in like what should this number be? Like how many points live in should live in a combinatorial rectangle? We can say some constant depending on L. What is the dependence on L? Other questions?
Is that really sharp in all respects? So, for example, if I wanted to ask the same question about the cubes, but saying when does it happen that 90% of the possible cubes will contain? If I relax that way, is it the same kind of threshold?
I see. That's a good question. That is studied, and I believe you can do better in that situation. I don't have the results off the top of my head though, so maybe ask me again later and I can do a quick lit review and get back to you. Cool. Okay, so I guess let me move ahead to the new stuff though, so as not to get sort of bogged down in the background. Yeah, but so this is the story so far. And again, the main takeaways that I wanted you to take from those previous slides are that all of these three questions, like to the extent that we know the answer, they look basically like this. So for the rest of the talk, what I'm going to do is first, I'm going to tell you that this threshold behavior is a very general phenomenon. And in particular, it holds for any local property, where local property is something I have to define. Moreover, I'm going to give you a characterization of this threshold. So I will tell you, like, you tell me something about the property, I'll tell you something about the threshold. And the third part of the talk is an application, like I said, some application to list decoding LDPC codes. But the sort of intuitive punchline is that basically it's carrying over some of these properties from the uniformly random case to the not uniformly random case. So LDPC codes, which I'll define later in the talk if I have time, are basically give us some structured, very structured ensemble of random subspaces. And what this third part of the talk is going to be showing is that if you have like a high probability result, like these results up here for uniformly random codes, so this says that, you know, with high probability, a random linear code, sorry, not uniformly random, random linear code will satisfy this property, or uniformly random subspace will satisfy this property. Then with high probability, this structured random subspace will also satisfy the property. So just a quick aside to kind of insert the concentration of measure angle here, because this is a workshop about concentration of measure. Basically what this is doing is allowing us to translate concentration of measure results from one setting to another. So like these results up here are concentration of measure results. Basically, you want to show that you know, certain properties hold with high probability in some random object. And the way these are proved, you know, use a lot of concentration of measure techniques. So lots of tail bounds, chaining arguments, stuff like that. And essentially what we're going to be able to do is transfer these concentration of measure results to a more structured ensemble where there's even less randomness. And we'll kind of get to do this for free from our threshold theorem. Cool. Okay, so that's sort of the outline. So let me get started with sharp thresholds for local properties. So what do I mean by a local property? And what is this threshold theorem? Okay, so what is a local property? So basically, intuitively, a local property is defined by the exclusion of bad sets. So a little more formally, suppose that curly B is a collection of bad sets, B1, B2, and so on. These are subsets of F to the N. So the following things hold. First, I want B to be invariant under coordinate permutations. So let me illustrate that with an example. So here's like a possible collection of bad sets here. So these are bad sets of size 2 that live in F2 to the 4. So here are like the dark squares are meant to be 1s and the light squares are meant to be 0s, I guess. And this set curly B is invariant under coordinate permutations. Because like if I look at this set B1 and I permute the coordinates, let's say I switch the second coordinate and the third coordinate here, and then I'm going to get, looks like B3. Right? And similarly, if I take any of these and I do any coordinate permutation, I'm going to always stay within this set. So that's the first thing. The second thing is that each of these bad sets B has size at most little b. So in this case, little b is just 2. Okay, so suppose I have this collection of bad sets, curly B, that satisfies these properties. Then a B local property, these are the sorts of properties I'm interested in, are going to be properties of the form, there is no bad set that is contained in my subspace. So that's the definition of a B local property. So in this example, it's like if I take a random subspace of F2 to the 4 and I ask like the corresponding B local property that corresponds to this particular bad set curly B is the property that none of these pairs of points are contained in this subspace, or equivalently, there is no X and Y in my subspace, so that X is the negation of Y and X has weight 2, which is just another way of describing this silly little set curly B. Okay, so that's what a local property is. That might seem like a funny definition, but actually we've already seen 3 examples of it. All 3 of my earlier examples are local properties. So distance at least delta n is defined by the exclusion of pairs of points that are too close to each other. List decodability is defined by the exclusion of, I guess, L tuples of points that all live in a Hamming ball. And list recoverability is defined by the exclusion, again, of L tuples of points that all live in some combinatorial rectangle. So this is I'd like to argue this is a pretty natural notion, and it covers sort of all of the coding theoretic motivation that I mentioned earlier. Cool. Okay, so with that definition, here's this threshold theorem that I promised. So the theorem basically says that for any local property, you're going to get this diagram that we had earlier. So formally, suppose that epsilon is greater than 0 for any B local property, P sub curly B on F to the N. There's some threshold R star right here, so that if you back off a little bit from R star, then you'll satisfy the property with probability 1 minus the low of 1. If you go forward, you'll satisfy the if you go forward by epsilon, so look at a slightly higher dimensional subspace, then with probability 1 minus the low of 1, you will not satisfy the property. Okay, so this threshold thing is pretty general. I think the more interesting thing, though, is that we can actually give a characterization of this threshold. So let me I'm going to introduce this characterization kind of by example. And in order to do so, I'm also going to make a couple of simplifying assumptions. So let's just assume that each one of our bad sets has size exactly little b, and also has dimension exactly little b. So in this case, each of these bad sets has size exactly 2 and also dimension actually exactly 2. In this case, just these 2 points these 2 vectors are linearly independent. Let's also, just for ease of drawing things, assume that the size of F is 2. And let's also assume that curly B contains only 1 orbit under coordinate permutation. So all of these assumptions can be removed. It's just going to make the exposition a little bit easier. So basically, we're just assuming that the situation looks like this little toy example curly B that I had before. Okay, so we would like to try to figure out, like, what is the threshold at which I become really likely to contain one of these bad sets. So the first thing we might try is a first moment attempt. Right? So we have some random k-dimensional subspace of F2 to the N, and we want to upper bound the probability that there exists some bad set in my subspace. So a very natural thing to do first is, like, let's just compute the expected number of bad sets that live in my subspace, And if that expected number is little o of 1, then by Markov's inequality, I probably won't have a bad set in my subspace. All right, so let's just try that, see how well that works. Okay, so let's do the computation. So for some fixed bad set, what's the probability that that bad set is contained in my subspace? Well, I claim that it's this thing, 2 to the k divided by 2 to the n. So this is the probability that a single point is contained in my random subspace, because there's 2 to the k points in my random subspace out of 2 to the n total. And then I can raise it to the b because I'm assuming all of these points are linearly independent. And so if I take a random subspace, the probability that each of them is contained in this subspace is independent as a random variable. So I can just raise it to the b. Okay, so that's just equal to 2 to the minus n minus k times b. If you didn't follow that, it doesn't really matter, but just I'm doing the straightforward calculation of computing the probability that a particular bad set is in a random subspace. Okay, so now let's compute the expected number of bad sets in my random subspace. So the expected number of bad sets is just the size of curly b, the number of bad sets, times the probability that each one of them lives in this subspace. Great. Okay, so now I can ask, when is it the case that this expected number is little o of 1? Not like that I expect there to be like no bad sets in my random subspace. Well, you can just solve for it. Like if I want this thing to be small, then basically what I want is that k divided by n should be a bit less than 1 minus log of b divided by bn. So that's just what happens when I set this thing equal to 1 and solve for it, and solve for k over n. Right? And then if we back off by that, additionally by some epsilon, we conclude that the probability that there exists a bad set that's contained in my subspace is by Markov's inequality at most the expected number of bad sets contained in my subspace, which by plugging this thing into that thing is going to be at most 2 to the minus epsilon n. So very tiny. Cool. Okay, does this make sense? Great. Cool, so let's call this threshold, or let's call this value here, let's call this the expectation threshold of curly b, or expectation of curly b. So basically this is the threshold on the ratio k over n, dimension of the subspace divided by dimension of the ambient space, sort of above which you expect there to be lots of bad sets in my subspace, a little omega of 1 bad sets, and below which you expect there to be little o of 1 bad sets in my subspace. So there's some threshold there. Cool. Okay, so getting back to our question of like, what is this threshold? What have we just learned? So we've just decided that by Markov's inequality, there's this very easy to compute threshold right here, this expectation threshold. So that if I back off by epsilon, it's really, really likely that I avoid all of the bad sets. And the question that we might be asking at this point is, well, is this the right threshold? Like, is it the case that the curve ought to finish off by doing that? Or might it be the case that I could go a little bit past that and the threshold is something else? Intuitively, like what it would mean if this were the case, like this would mean that the expected number of bad sets in V is really big, but the probability that there exists a bad set in V is really small. So this might happen, for example, if there are some subspaces V that contain tons and tons of bad sets, but most of them don't contain any, right? That would be consistent with a curve that looks like this. Or another way to say that is like once a subspace V avoids one bad set, it's sort of preternaturally likely to avoid a bunch of other bad sets. These events are sort of clustered in the subspaces. So this is the question that we have, like, is this the right threshold or is it something else? Question make sense?
So there is this, I don't know if it still is, a conjecture of Kahn and Kalai, right? That the true threshold is, I guess, for every monotone property, some log factor times the expectation threshold. Is that a reasonable intuition to have in this context as well? I think they might have said that in the context of random graphs.
Yeah, so actually we're going to get something very similar to the sorts of things one can get in random graphs here. Yeah, okay, so spoiler alert, the answer is this is not the right threshold. You can go a little bit beyond. Because we're looking at very specific properties and not just like any monotone property, we're going to be able to get like much tighter maybe after I finish saying what our result is, I will mention the relationship to like this sort of flavor of random graph results, because they are very similar in spirit. Yeah, it's a really good question. But yeah, I guess the short-term answer is that yes, definitely related, because we're looking at much more specific properties. We're going to be able to get like much more specific answers. Cool. Okay, so yeah, okay, so I guess I spoiled it. The answer is that you can go a bit beyond this, and let me show you an example of how that can happen. So here's just a simple like toy example of how you can like go beyond this expectation threshold, how that first moment argument does not give the right answer. So suppose that my bad set B is all of the coordinate-wise permutations of this thing. So here I have like three vectors. So I have a little b is equal to 3. And I'm looking at all of the vectors where a quarter of the coordinates look like 1, 0, 0, a quarter of the coordinates look like 1, 0, 1, a quarter look like 0, 1, 0, and a quarter look like 0, 1, 1. And then just like look at all the coordinate permutations, sort of close this under an orbit, and like that's my bad collection. And I just want to know what's the probability that a random subspace avoids any triple of vectors that looks like this. Okay, so we can do this computation and we can figure out what this expectation threshold is. So the size of curly b, well, it's about 4 to the n. Roughly, there are like 4 possible choices for each column or for each row here, and I get to pick n of them. And then, okay, it's not exactly right because they all have to be exactly n over 4, but close enough. So, okay, so there's curly b has about 4 to the n things in it. So then the expectation threshold is going to be just plugging in what we got when we did that computation from the previous slide, 1 minus the log base 2 of the size of b divided by 3 times n, which is roughly 1/3, using the fact that the size of b is roughly 4 to the n. Okay, so that tells us that we have this picture here. If I back off by a little bit from 1/3, so look at subspaces of rate or of dimension a little bit less than n over 3, I'm with really high probability going to avoid all of the triples that look like this. Okay, now consider what happens when I just ignore this third vector. So I'm going to look at a different collection of bad sets. This collection is going to be curly b prime. That's just given by dropping the third vector, right? So I'm saying my new bad collection is all pairs of vectors, basically that have n over 2 of the coordinates that look like 1, 0, and the other n over 2 look like 0, 1, scrambled up in some order. We can ask, once again, what is the probability that a random subspace avoids all of these guys using our first moment type of calculation? So let's just do the same thing again. Now the size of curly b prime is like 2 to the n. There are 2 possible choices. I get to choose n times. So we can just compute this expectation threshold. It's 1 minus the log base 2 of b prime divided by 2n. Here, this is 2 now because there are 2 things. And this is about 1/2, which is notably larger than 1/3. So what this means is that if I back off from just 1/2 by just a little bit, then all of a sudden it becomes really likely that a random subspace of rate, 1/2 minus epsilon is going to avoid all pairs of points that look like this. But in particular, if it avoids all pairs of points that look like this, then it's certainly going to avoid all triples of points. So that means that like even if I go all the way out to here, like well beyond this 1/3 threshold, it becomes really likely that I will satisfy my original triple property, even though this is like way beyond what that expectation threshold was for the triple property. So going back to this slide, the answer to this question, does this always give the correct threshold, is no. In fact, it can be the case that this sort of thing happens, that the expected number of bad sets is small, but the probability, or sorry, that the expected number of bad sets is large, but the probability that there's any bad set is still small. So this can happen. Okay. Did that example make sense? Cool. Okay, so now I can sort of get on to our characterization theorem. So theorem, here's the informal version. This example is basically the only reason why that first moment method is not the right answer. So this example is the only reason that expectation threshold is not the right threshold. So what do I mean by that? So what went on in this example, we had some set that we are interested in, and we projected it down by like forgetting one of the elements. And we made this new set b prime. we observe that if V, a subspace, avoids B prime, then it definitely also avoids B. And somehow the size of B prime ended up being like smaller than you might think. So therefore, by Markov's inequality, you're more likely to avoid it than you might think. And thus, going backwards, I'm more likely to avoid this original set than I might think. And so I claim that basically this is the only thing that can be going on. Right? I need to generalize it just a little bit. So let me write this projection here, not as just like dropping a thing, but I'm just going to write it as multiplying by some projection matrix. And then I'm going to generalize just a smidge by replacing this projection matrix with any old matrix. And now this is actually as general as I need to be. Like this is sort of the only reason that the expectation threshold is not the right threshold. Is because there's some little matrix A here that I can multiply by to get some set curly B prime, so that curly B prime is smaller than you might think. Or equivalently, that the expectation threshold for curly B prime is larger than you might think. So a little bit more formally, although I guess still with pictures, suppose that curly B is a single orbit under coordinate permutations. Then the threshold rate, R star, is equal to the maximum over all matrices A. So just take the, I guess, worst or best, depending on whose side you are. Let's say best matrix A. And look at the expectation threshold of what happens when you take your original set curly B and you multiply it by that matrix A. Right? And that's going to give you the threshold. That's for a single orbit. If you have a property that you're interested in that can be characterized as the union of orbits under coordinate permutations, then you basically just look at the worst orbit, and that will give you the threshold. So do exactly the same thing for each orbit and look at the worst of them. So that's the theorem statement, sort of for the characterization of this threshold. Are there any questions at this point?
Do you have some characterization of when you don't need an A to project down?
Do you mean like when I can just use a coordinate projection, or when I don't need anything at all, when the expectation threshold is actually right?
Yeah, the latter.
Oh, that is a good question. So I guess I can plug some recent work with Venkat Guruswamy, Ray Lee, Jonathan Moshev, Nick Resch, and Shashwat Silas, where we sort of applied these types of techniques not to random subspaces, but just to completely random sets. And in that case, you can actually show that like you don't even need, then the expectation threshold is kind of exactly right. For random subspaces, it's a good question. I don't have a good answer. So I will think about it. Other questions? I think at this point I have a hidden slide which addresses one of Prasad's earlier questions, which is the analogy to random graphs. So let me, somehow it stopped showing my screen when I went to hidden slide.
Yeah, I checked quickly. They do in the end a fractional expectation threshold. This is what something Talleyrand had mentioned, I think.
I see. Okay. Yeah, I'm not familiar with the work in particular that you mentioned, but here's sort of like something in general to like connect this to results of a similar flavor that are proof for random graphs. Like the type of statement that you might be able to make for random graphs is that like you might ask like when is H, some subgraph H like likely to appear as a subgraph of GNP? And the answer is like when P is large enough so that for every subgraph of H prime has an expectation omega of 1 copies in G. And this is basically an analogous statement to that. Like when is a particular bad set or bad collection B, or if it's a single orbit, likely to appear in a random subspace V? It's when the dimension of V is large enough so that every like linear, or I should say linear projection curly B prime of B has an expectation omega of 1 copies in V. So it's very similar flavor to the types of statements from random graphs. So hopefully that answers some questions. Cool. Okay, so I guess let me, well, I only have 10 minutes left. Or when should I stop talking?
Yeah, you have 10 to 15 minutes, depending.
Okay.
Since we are interrupting you, asking questions, you can go until 5 to.
This sounds good. Well, hopefully I will be able to wrap up in 10 or 15 minutes or so. That problem. So now we've done through the main meat. Yeah, so the proof of this statement, I'm actually not going to talk about it, which is why I will be able to wrap up in 10 or 15 minutes. It's not so hard, actually. It's just the second moment method. I direct you to the paper for the details. But I think really the hard part is coming up with the right thing to look at, which in this case is these sort of orbits under permutations and these linear projections. And once you kind of know that that's what you're going for, and you know you're supposed to use the second moment method, it's kind of works out. So I'll direct you to the paper for the proof, but yeah, basically just the second moment method. Okay, so in the last part of the talk, the remaining 10 or 15 minutes or so, I want to talk about applications of this characterization. So I'm going to mention 3 applications, then only talk about one of them. So the first application, which I've mentioned before, is the listed codability of random LDPC codes. There are 2 other applications, which I'd point you to this paper for these 2. This is joint work with Venkata Ramaswamy, Ray Lee, Jonathan Moshev, Nick Resch, and Shashwat Silas. And there we can sort of use this characterization to actually study random linear codes themselves and get better bounds on the number of points that are likely to live in any ball or in any combinatorial rectangle. But for now, I want to focus on this first point, the list decodability of random LDPC codes. And so let me say a little bit by what I mean about that. Okay, so what is an LDPC code? So LDPC stands for low density parity check codes. So basically, like going back to that coding theory jargon that I brought up at the beginning, the idea is the following. Like suppose instead of just taking a random subspace, you take a subspace that is the kernel of a random sparse matrix, sort of random according to a particular distribution. We consider something called Gallagher's ensemble of LDPC codes. This is a very like classical distribution of sparse matrices. It was sort of defined in the 60s. And the reason people look at these sorts of things is that if you're using such a subspace for communication, so each point in this subspace corresponds to a message that you want to send, then if you receive a perturbed version of this point, you want to be able to round back quickly. And it turns out that if the subspace that you're looking at is a uniformly random subspace, then this is conjectured to be an extremely difficult problem. However, if the subspace that you're looking at is the kernel of some sparse matrix, then it turns out that there are efficient algorithms to do this. So there's very fast, what's called unique decoding algorithms. And for this reason, LDPC codes are ubiquitous in both theory and practice. So it would be really cool if we could extend these results for uniformly random subspaces to these sorts of subspaces, which are not uniformly random. They're much more structured. In particular, the question that we were interested in is, are these things list decodable? So that was the question of are there too many points that's contained in any Hamming ball? Right, so the math question here is, instead of a uniformly random V, you have this structured random subspace, so the kernel of some sparse matrix. I'm going to just call this subspace a random LDPC code. And I want to know what's the probability that no L points of V are contained in any Hamming ball of radius Pn. So that's the question. Okay, and so here's a theorem that answers this question. Suppose you have some B local property, like list decodability, that we've already looked at. Let epsilon be greater than 0. And suppose that a random subspace of dimension r times n satisfies this property with high probability. Right, so in the picture that we had here, we know that a random subspace, a uniformly random subspace, is going to have a picture that looks like this. So if a random subspace satisfies this property with high probability, that means that R is a little bit less than some R star. So we're in this regime over here. Then the conclusion of the theorem is that a random LDPC code of dimension a little bit less also satisfies that property with high probability. So that is, we can sort of bring the positive part of this curve, just bring that to random LDPC codes. So the probability that a k-dimensional LDPC code satisfies this property is also high. So a useful corollary of this is that random LDPC codes are list decodable, okay, so this is some jargon, up to list decoding capacity. So basically there's been a long line of work which establishes that random linear codes, aka uniformly random subspaces, have basically optimal trade-offs for this how many points live in a ball type of question. And now for free, we get those results translated to these much more structured codes. Okay, so this is the theorem. I want to say a few words about the proof, but are there any questions about the statement?
So this is a one-sided statement?
You mean like
the purple
I only
curve?
have a purple line here and I don't extend it down there?
Yeah.
That's right. Yeah. So this is a one-sided statement. It's a really good question whether the converse is true. So actually the converse is false, but it's false for stupid reasons. For this particular ensemble of LDPC codes, for this particular ensemble of random matrices, like you can set up the parameters so that there are no odd weight vectors that live in this kernel. Like if you set things up to be regular enough with your sparsity pattern, then you can rule out odd weight vectors appearing in the kernel. But of course, it's extremely likely that an odd weight vector will appear in a uniformly random subspace. So that will kind of break, like that silly example kind of breaks the converse, but it seems plausible that you can formulate some kind of converse that rules out like silly sort of divisibility, things like that. Yeah, I do think the converse is true. Just you have to like rule out certain bad cases. Yeah, that's a great question. Other questions? Cool. Okay, so let me say just a little bit about the proof. So I claim that this basically comes for free from this characterization that I just told you. So here's why. Okay, so first we need a lemma. So the lemma is the following. So subject to some fine print, the probability that a particular bad set B is contained in a random LDPC code, so that is the kernel of this sparse, random sparse matrix according to this particular distribution, is approximately 2 to the minus 1 minus epsilon times n minus k times b, where this epsilon here depends on the sparsity of the matrix and some other things. And the thing that's notable about this is that this is basically the same as for a random linear code, or sorry, for a uniformly random subspace, right? Before when we did this computation for a uniformly random subspace, we just like, didn't have this 1 minus epsilon, but just everything else was exactly the same. So intuitively, that means that, okay, so if curly B is unlikely to appear in a uniformly random subspace, then what we just showed in this characterization theorem is that essentially there's like a first moment reason why that is true. Right? Essentially, there's some projection A that gives you some smaller like curly B prime, so that curly B prime just by Markov's inequality won't appear. But then that same first moment reasoning is going to apply to random LDPC codes, because we just showed that this, or I just stated that the probability that any particular bad set is contained in a random LDPC code is basically the same as for a uniformly random code. So any sort of first moment argument you want to make, Markov's inequality, expectations, stuff like that, is going to work just the same for an LDPC code as it does for a uniformly random code. So that means that this reason here, like there exists this B prime such that blah, 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 you can still make that argument for the random LDPC code. It goes through just the same. So then we conclude that curly B is also unlikely to be in a random LDPC code. Or I guess in more detail, we'd conclude that curly B prime is not going to be in this random LDPC code, and then therefore curly B is not either. So this just goes immediately from that. So how do we prove the lemma? Just I guess some real quick intuition. Like the probability that a particular bad set B is contained in a random LDPC code. This is the same as the probability of B times this sparse random matrix is equal to 0, that all of these columns of B are contained in the kernel of this matrix, right? So here I'm viewing a bad set as a matrix, thinking of the columns of this matrix as the elements of my bad set. So all of these things being in the code is the same as when I multiply by this called a parity check matrix, I'm going to get 0. Okay, so let's focus in on just one row of this. Like, what does it mean for one row of this thing to be 0? Basically, it means that for sort of a random subset of rows of this matrix B, the ones that are picked out by these ones in the matrix, that those are going to add to 0. And in the particular distribution that we're looking at, these ones are sort of random enough that you could basically use some Fourier analytic argument to show that, provided that this set B is not too pathological, then if I take a sum of a bunch of rows, the probability that that sum of a bunch of random rows is 0 is about what it should be, which is like 2 to the minus b. And then you have this little 1 minus epsilon fudge factor, which depends on the number of random rows you take. This works as long as, I guess, the columns of B aren't too close together, or actually it should be that nothing in the span of the columns of B are too close together. But it turns out that we can sort of rule out that bad case separately. It's well known that LDPC codes have good distance, which in particular means that none of the things in it are going to be too close together. So you can ignore those other B's, and for all the rest of them, this sort of basic argument that if you take a bunch of random things, it's kind of going to even out works pretty well. Cool. Okay, so that's basically all I'm going to say about the proof of this theorem. But again, the corollary is that these results that people have sweated very hard to prove for uniformly random codes now come just sort of kind of for free for more structured ensembles like random LDPC codes. Okay, so let me wrap up quickly. So just to recap, I started out the talk by asking like what local properties are satisfied by random subspaces. There's a whole bunch of local properties that you might be interested in from the context of error correcting codes, and maybe there's some other local properties that you're interested in. I told you that theorem local properties have sharp thresholds. So for any local property, there's some R star below which you're very likely to satisfy the property, above which you're very likely not to satisfy the property. I told you that this threshold has a nice characterization. Basically, this first moment approach is almost right, just with one little tweak. And in particular, that gives us some applications to list decoding random LDPC codes, basically allowing us to say, well, if the first moment's all you need, well, at least we have the first moment stuff for random LDPC codes, so let's just do that. So that allows us to translate these results. Cool. Okay, so let me conclude with just a couple of open questions. The main open question, I think, is what are some other applications of this characterization? So I mentioned 3 and discussed one in detail, but all of these applications are to error correcting codes, because that's what I think about most of the time. So I'm sure maybe this audience would have different ideas of applications, and I would love to hear them. And the other big open question is algorithms for list decoding LDPC codes. So my motivation for studying LDPC codes was that they have efficient algorithms. They have efficient algorithms for unique decoding. That's when I happen to know that there's only one point in the ball. But if I want to say you give me the center of a Hamming ball, and I'm supposed to tell you all of the points in this subspace that live in that Hamming ball efficiently, ideally in linear time, I don't know how to do that. So what we've shown is that it's at least in principle possible. Like there's not an exponential number of points you have to return, but actually coming up with an algorithm, I think is a really nice open question. Okay, so I think that's it. So with that, I will stop talking and take any more questions that you have.
Thank you. Thanks very much. Let's clap. Any questions? Any more questions, I should say? I have a couple, but I'll hold on.
For the B local property, it is invariant under all permutations. Would it work if it was invariant under like a subgroup of permutations?
That's a good question.
Or just if you have like some symmetry but not like the full yeah.
Yeah, so the reason we need the symmetry is basically the way the proof goes is we kind of break things into these orbits and kind of study them orbit by orbit, and then it's very easy to get a handle on the number of things in that orbit if it's just all the permutations. I think that, yeah, so I haven't thought about it. It feels like something should still go through if you have some other symmetry group that you're looking at. But yeah, I haven't thought of it. Is there a particular application that you have in mind for why that would come up?
No, it's just I guess I could imagine situations where you don't have the full symmetries, but you still want to have a sharp threshold. So.
Yeah, it's a good question. Yeah, I don't know the answer off the top of my head. My gut says that maybe something should, the ideas should basically go through, but I haven't tried it.
So the characterization itself is that if you have this sharp threshold, as long as you don't contain such a property, right? Something that's bounded by B and invariant.
That's right. Yeah.
Yeah. So so I didn't want to ask this earlier because I thought I might confuse everybody. So being familiar with the Ehud-Friedgut's theorem and about sharp threshold in the context of random graphs, random structures. So the way I think about it is that basically any global property is expected to have a sharp threshold in the sense as that people define in random graphs. So that's why here it confused me just the terminology.
Oh right, this is a local property instead of
right.
a global property. Yeah, that's
the intuition is that if there is not containing a triangle or a fixed finite list of fixed subgraphs and so on. So just the terminology, yeah.
Yeah. Oh, yeah. That's right. I guess that is.
But the other difference, I think, to me, a more important difference seems to be, of course, the models are different. There you have sort of full independence by picking each edge independently and so on. But there, the notion of sharp threshold is also a bit different, right? So you measure the slope of this curve with respect to where it happens. So you look at sort of, right, you see the R star, so to speak, or
right.
P star, the probability where you expect the property, typically the monotone or non-monotone, if it's gone from 1 to 0, so the anti-monotone property, where it goes from 1 minus epsilon to epsilon. So you put yourself at 1/2, let's say, and then you ask yourself, how sharp is the threshold? But here, you don't define it that way, right?
That's right. Yeah, I guess maybe we're looking at sort of a less refined version of thresholds. We're just saying like go epsilon in this direction should be. I guess in the slides I just said 1 minus little o of 1, but it's
right.
It's 1 minus 2 to the minus epsilon n. The sort of thing. But yeah, we're just sort of looking like what is this? We're more interested in what is the threshold rather than the exact slope. But yeah, it's an interesting question.
Yeah, the finer one seems actually quite a bit. Many years ago at Microsoft, Ehud, Jong-Han Kim, and I spent some time trying to work with the finer notion, and even to prove things like if I start picking vectors of weight k, can I show that there's a sharp threshold as to when I lose independence? Right, at some point I go from being independent to dependent.
Yeah.
Turned out to be quite non-trivial. So, but I think this looks like actually a nice set of results, which maybe gives hope to attack the finer sense of thresholds.
Yeah, as someone who's thought a lot about like random subspaces and like when you have these sorts of results, I guess mostly from the context of coding theory, somehow this way of thinking about it feels more right to me than previous ways of like breaking it up into these sort of orbits under permutations. And yeah, I'm hopeful that there are going to be other applications of this framework as well. So if there are questions about random subspaces that are still nagging you, I would love to hear more about them.
Sure. By the way, I just posted in the chat the link to this paper I was referring to.
Oh, awesome. Thank you.
That was, Any other questions from folks?
I had a small question about the amount of randomness. So
Go ahead.
yeah, you assume it's a uniformly random linear subspace. Do you need that much independence, or let's say, I mean, if it has size B, is the B-wise independence sufficient for the proof to go through, or even less? What? Yeah.
Good question. I mean, so in some sense, the third part of the talk is almost like de-randomizing this result, is saying like instead of looking at a uniformly random subspace, you're looking at the kernel of a much more structured matrix. So that uses a lot less randomness. In terms of whether such a threshold result would hold if you just had B-wise independence or something. I don't see, or like, I don't see why not right now, or maybe two B-wise independence for the second moment method. They need to look at pairs of them. But I'm probably missing something silly. Good question. Yeah, I don't know off the top of my head. I don't see right now what would break. I guess one thing is that we might be able to, all right, so now I'm like going out on a limb because I haven't thought about whether or not this is true, but if that is true, it might be that then you could prove this sharp threshold theorem, but unfortunately you couldn't understand where the threshold was. So like these other results of like, when is a uniformly random subspace list decodable, those results definitely do not work with limited independence. And so those are the results that we're kind of like harnessing, and then we're using this characterization theorem to like bring those through. So if you were to start with a limited randomness thing, like it might be that we wouldn't be able to get a very good handle on the thresholds to begin with. But maybe it would prove that they're worth sharp thresholds. I don't know if that answer made sense.
Yeah, thank you.
Any more discussion or questions? If not, let's thank Mary again. And also there's the GatherTown link Omid had shared with us earlier. So feel free to continue discussion there. Thanks again, Mary. Nice.
Thanks everyone for watching. Bye.
Good to see you again. Bye-bye.